spoke on integrative AI within the FAIR project. Yesterday, I believe it was an interesting day. In the morning, we had a presentation about the scientific impact of the research that we do in FAIR in this spoke. Some presentations were given by excellent, I would say, excellent young researchers who have been hired in FAIR. In the afternoon, we have a very interesting discussion, I believe, with companies. This is very important because also we discuss the role in the market that this company can have on a technology that nowadays we know USA and China, of course, are really investing a lot and providing incredible results. But there is still a market from them, from the discussion. And also we had an evidence that FAIR, in some way, provides a way to foster this market and social impact. In the second day, we will have the morning session that will be dedicated to our new partners. The University of Bolzano, Padova, Udine, Torino, and Verona, with 2 different projects in 2 different departments. As I mentioned yesterday, this is the result of a cascade call for university. The call was launched at the end of the first year in December 2023. And we managed, this is a big result, a big administrative result, to complete all the process. So evaluation of the proposal, selection, contract signing by the spring of the second year. So all of them can start. I believe this is a very important section because it allows to join the forces with the top-level excellent groups in different universities. And now I hand over the floor to Alessandro Sperduti. We will moderate very strictly, taking into account the time, this new section. So thank you very much.
In a muscular way.
In a muscular way, yes. Mi levo,
Perfect. I checked before and it worked, okay? Okay. Now everything is okay. Okay, I'll do it right this way. Okay, that's more or less. Yes, okay. The problem is called MapSat, and the main theme is the design and implementation of solvers for computational logic and automated reasoning, able to take advantages of modern CPUs, so parallel devices developed initially for graphic processing and in the last decades used for more general purpose computations, as everyone already knows. Okay, the project started a bit later than the other, I suppose. We started in June for some bureaucratic problem. I don't want to go into details, and involves people from two departments of the University of Udine, from the Department of Science, let's say, and Computer Science, and Department of Engineering. Okay, so as I said, one of the lines of research consists in parallelizing basic tasks that you can find in solvers for computational logic. For example, if you think about a SAT solver or an ASP solver, an ancestor programming solver, which is very similar but a bit more tricky, you can find some basic functions, the one devoted to the learning step, the one devoted to the conflict analysis, unit propagation, and so on. and we want to obtain a GPU-oriented versions of these modules. Okay. On the other hand, we want to face another problem, which is the one of realizing, again, a GPU-based implementation of some other kind of modules that perform some sort of domain-specific reasoning. So, for instance, the decision procedures that one can use in SMT, or the propagators that one can use in CSP solvers, and so on. Okay, that's one. That's I would say the main stream of research of the project. And the aim is to use these modules, at least in two different ways. One is to obtain a toolkit of modules that one can use to enrich an existing solver, for instance, plugging in some GPU-based functionality, which could be seen as a substitute of the functionality of the solver, or a companion of that functionality, and the solver could decide at that time which one is better to use. And the final goal is to obtain a full-blown GPU-based solver for ASP initially, which in a sense includes a SAT solver inside, and an extension of solver for constraint satisfaction problem using the modules that I mentioned before. So this is more or less the goals of the project. Okay, just a slide to rewind very briefly and very imprecisely what is a GPU. A GPU is a bunch of cores, thousands of computing units, to be correct, because there are not only cores, but there are other things that can that compose the hardware, and a hierarchy of memories, different kind of memories with different size, different efficiency, different pattern, access pattern, different lifetime, very different one from another. And this device is controlled by the CPU, which in the terminology given by CUDA is called the host, while the CPU is called device. And in the simpler interaction, the CPU transfers data from and to the device and runs computation on the device. That's the simplest way in which the two devices interact. Okay, the computational model is called single instruction multiple thread, very similar to single instruction multiple data, but a bit different because we have a number of threads executed by core, but each thread has its own execution context. So, in principle, they can execute different instructions. You can have 1,000 threads, each one executing a different instruction. Threads are organized in groups called warps, blocks, and grids, and each of them has its own peculiarities and synchronization and communication constructs, and so on. Okay, just another slide to single out what's the difficulty in programming this kind of devices. If one wants the maximal performance, has to adhere to some directives. The first one is all the cores must execute the same instruction. As I said before, this is not mandatory. But if you don't do it, you obtain serialization of executions, so performance decreases. Okay, so the idea is, if you execute on the CPU, be sure that many threads execute the same instruction. Okay, I'm simplifying a lot, so I'm not very precise in saying that, but just to give the idea. Moreover, we have a number of different kind of memories, and the way in which the threads interact with these memories is different depending on the memory. So we have different pattern access to be used, depending on which memory you are accessing and so on. Different sides of memories. Different mechanism for synchronization and communication between threads, depending on which group of thread you are considering, warp, block, grid, and so on. Okay? So you have to take account of many things, and what turns out is that if you take a parallel program developed from another kind of architecture and try to run it on this device, probably you succeed in running it, but the performance will be very poor. Okay? So we have to face these difficulties. To realize the goals that I said before, we started working on this, and we obtained we made some initial steps. The first thing that one of the things that we did, and we are still doing, is the development of ASP SAT solver. We started from the analysis of what's on the shelf now, what are the state-of-the-art solvers, mainly for ASP, singling out what are the best use of memory, of the GPU memory, to support the functionalities of these solvers, and started to implement. Okay, we are not we're not finished, of course, but the first thing that we notice is that there are two functionalities that in the standard solver, in serial solver, let me call them like that, are very efficiently implemented, which are the conflict analysis functionality and foundness enforcement for ASP, which are very efficiently implemented in existing solvers, but the algorithms that are used are not parallelizable. Okay. Still? Okay. So we had to develop a new algorithm for these functionalities. We are implementing them. Okay. On the other side, as regards CSP, we started developing a number of GPU versions of propagators for global constraints, for common global, very used global constraints. The first one we did was the cumulative global constraint. The trail we followed was to the same, look at the algorithm that exists for solving this problem, select, study, and design a GPU-based version of the best parallelizable option, do it, implement it, integrated it in existing CSP solver. In our case, we choose mini CPP, and validate, okay. For the cumulative constraint, we also have a result published on journal recently. And so it seems to work. So we started working on other constraints. We are completing the table, global constraint, the same sequence of steps, more or less. And we are also working on another constraint, which is called the stable marriage global constraint. Okay. Also, this is being implemented in CUDA, integrated in the mini CPP solver. Okay, in doing all these integrations of propagators, we also developed a sort of uniform way of acting. So a uniform interface, a uniform recipe to follow. Very simple, actually. You have to produce two methods to handle your constraint. You can invent one, and then plug it into the solver, extending a syntax of the input language, the modeling. Okay, that's all. So you can do it very uniformly for various kinds of constraints. And we are, okay, refining this interface now. Okay, what is ongoing? I almost finished. Developing the lines and the things that I mentioned in the previous slides. Okay, so I don't read the lines, but this is the the summary of what I've said in the previous slides and what we are doing now. Okay, and that's I'm done. That's all from me.
Very good. So while Padova, so Nicolò is going to prepare the presentation, we can also have one question. Can I ask a question while I'm moving?
Yeah. Here are the steps.
What is the speed up factor you got in solving?
It depends. It depends on the constraint, of course.
Okay.
I'm thinking about the CSP. Okay. It depends on the size of the instance that you are solving, and what turns out is almost the same scenario. If you have to do small, easy computations, it's better to do it on the host.
Okay.
Okay. If you have a big data to be crunched, then move it on the CPU. That's
Makes sense.
Any other question? No? Okay, thank you again. Nicolò?
Okay, good morning. I'm here presenting the project Symbolic Conditioning of Graph Generative Models from the University of Padova. The general idea of the project is to integrate domain knowledge in the broad sense, so in the form of constraints that can be expressed in many ways, in machine learning models, but in particular in machine learning models for graphs with a focus on generative ones. Our project relates, of course, with integrative AI in many ways. There is the idea to integrate AI with formal methods. I'm going to talk a little bit more about this later. Integration of domain knowledge, again, in many ways. In neurosymbolic AI, for instance, using knowledge graphs or exploiting large language models. And also trying to integrate constraints in explainable AI. Again, I'm going to talk a little bit about this later. This is the research team. So as you see, we are many people. In particular, we have 5 professors from Padova, of course, each one more or less with different competencies and background. And on the project, we hired 4.5 postdocs that started on the 1st of October. So actually, we started to produce more research since that day. So the presentation is organized in 2 parts. First, I'm going to speak a little bit about the theoretical contributions we are working on, and then I will try to present you the case studies, some of them if Alessandro stops me before. I will try just to give you the main ideas, hopefully trying to foster some collaboration. So if some of you is interested in some of these topics, either come talk to me, and there are actually many people from the project here, so you can talk to them. From the theoretical side, I'm going to present 3 ideas. First, we are working on some techniques to include constraints in neural networks in general, either in a hard or soft way. Then we are working on defining powerful graph neural models that can be used as a building block for generative models. And we also are working a bit on trying to identify some new formalisms to express domain constraints. So first about the inclusion of constraints in neural networks. So we are working on a project in which we are trying to enforce hard constraints in neural networks. So basically to produce a certification for the network to require specific constraints expressed in logical formulas. Now this is a hard task because traditionally formal verification methods, they are able to tell you if a network respects or not a certain constraints, but not to fix it. So we work in this direction. So given a network, we are able to basically modify it in such a way that we can guarantee it respects a certain constraint. Now, here you see the details, but I guess I don't have much time to go in it. The core idea is basically we generate counterexamples using a constraint satisfaction problem properly defined, and then basically retrain the network iteratively until we converge. In some cases, we can guarantee that we converge. Of course, in general, it depends on the property and on the network. Okay, this work is already published. Then, second theoretical part, graph neural networks. we are considering, so again, this is an example. We are working in a particular kind of networks that are called the CANs, Kolmogorov-Arnold networks. So the idea here is that these networks are not based on the, they're not defined in the usual way, but instead of having nonlinearities on the nodes, basically we will learn the nonlinearities on the edges of the network, so on the connections, and the nodes are fixed, they just sum the inputs. Now, the very interesting part of these networks, so from the performance side, there isn't much of a difference compared to the classical one, but the nice thing is that the functions that we learn are actually univariate, and they're modeled with relatively simple B-splines. And so if there is a symbolic representation to learn, what we are showing is that these kind of networks are able to learn it. Now, this is actually what was already present in the literature, so again, I don't have time, but the point is that these kind of models are able to extract a symbolic formula. What we are doing is we are extending this idea to work on graphs, and in particular, on dynamic models on graphs. For the moment, we are working with a fixed topology where the label of the node changes, but of course, the idea is to work on fully dynamic graphs. So we defined what we call a graph-can ordinary differential equation, where the idea is that we use these interpretable can methods to approximate a differential equation defined on graphs. For instance, for the moment, we are focusing on the Kuramoto model. And so, yeah, we can learn an interpretable versions of this graph dynamics. Third, theoretical contribution. So we are trying to, let's say, apply the category theory to artificial intelligence. So category theory is a very broad mathematical area, but what we are interested to in this project is that we can exploit this to force compositionality in different ways, actually. So on one hand, in the network design per se, so we can force that what the network learns is compositional, again, of course, if this is true for the domain. Or we can force it also in the explanation that can be generated for a particular model. So in the slide, you see a very simple example. So the XOR problem is, by definition, compositional with respect to the threshold function. So if we know this, this is the main constraint, and we can force it in the function, in the method we are using to learn the function. Okay, so now I'm going to present some case studies. Again, we are in a preliminary phase at this point. The core idea is to identify possible application areas in which using structured representation, so graphs, and constraints can make sense, can be promising. In this presentation, in particular, I'm going to talk to you a little bit about business process intelligence, embodied AI, and large language models, if I have time. So for what concerns business process mining, actually, there are a lot of possible applications. In this slide, I'm showing you a simple one. So the idea is that we have a data set of traces that are basically sequences of activities. And what we want to do is to do the data augmentation, for instance, if the data set is unbalanced. Now, the problem is that traces, so business event logs, are particular. And if you apply standard machine learning data augmentation techniques, they don't work that well. And the reason is that actually there are many domain constraints here that probably we don't know, but that actually exist for the model. So usual data augmentation techniques, of course, they don't consider them. So at the moment, we are working with an ad hoc approach, let's say, so an algorithm that starting from data generates reasonable, let's say, new examples. But the idea is that we want to be a little bit more general, so exploit generative models and try to enforce domain constraints that can be either automatically discovered from data. For instance, that is declared that is a formalism that is used to express constraints that can be learned in a data-driven way, or provided by domain expert or being common knowledge. A second, so staying on the same domain application, there is another interesting application area that are called object-centric processes. So the idea is that traditionally in process mining, we are considering each process in isolation, but actually life doesn't work that way, in the sense that in the same company, different processing can be running at the same time, and of course they can interact with each other. For instance, the same resource can be doing 2 different jobs at the same time, and so of course this slows him or her down. So the idea is that we can model these interactions between different processes in order to basically better model the reality and so provide better predictions, for instance. So the graph part here is clear, and also the part with constraints, because also in this case we can include the domain knowledge. Okay, also in the domain of process mining, we are trying to understand if including the domain information available in language models can help for in simple tasks of prediction. For now, we are considering them. The idea is that basically we can use language model to perform few-shot learning, like I said, for simple predictions models. And the idea is that this can help because in the processes, they are modeling real-world processes, and so we can have a description of each activity, and this description can be, for instance, textual, and so it can be exploited to include additional knowledge. Okay, a second application area is embodied AI. So in this case, we are working with robots, even though we are in simulations now. And in particular, a simple task is robot navigation. So basically, we have a sequence of a task that requires the robot to reach, for instance, different objects. The environment is not known a priori, so the robot has to move around and discover it. And the interesting part for us is what is referred to as social navigation. So the robot is not by himself, but it has to consider interactions, for instance, with other robots or with people that can be around. And in this case, of course, the constraints are clear because we have safety constraints. For instance, we want the robot not to hurt people in the house, of course. Or again, we can have external knowledge, for instance, on how to perform some tasks or some peculiarity of how to perform some tasks in that particular environment. In this case, graph representation is very helpful for having a high-level representation of the environment. For instance, topological maps. Yesterday, we have seen some works from the Spoke that worked on this idea. But actually, there are many ways in which we can represent the graphs here because this kind of task involves planning. And so we can also use the graph to represent both the environment and the possible actions that our robot can perform to actually use real planners and not just, for instance, language models. Okay, so I was quick, so I'm happy. The last application areas we are working on is trying to identify some limitations of large language models in order to, of course, try to improve these models using, again, domain knowledge or, in general, adding constraints. So actually, the focus here was to find some cases in which language models somehow failed for some definition of failing. And we started from a work done by our research group before for the idea. So the idea was that we noticed that the language model struggles to learn algorithmic procedures requiring propositional rules. So in particular, we now focused on the problem of formula simplification, so actually relatively simple. And the idea is that we are generating synthetic benchmarks to figure out what happens. And in particular, we identify 2 very simple cases that they don't require much reasoning, actually, but on which language models don't perform well. The first one is if we ask the model to change the priority of the mathematical operations, for instance, we say, okay, we have this equation, please simplify it, but consider that the plus has priority over multiplication. As simple as that. And the second one is if we use non-standard operations. I get some examples now. Identify the problems. We are now starting to work on some solutions. The simplest one can be few-shot learning, so including some examples in the prompt itself that can work somehow, but not that well. Or, of course, fine-tuning the models. So I conclude the presentation with a couple of examples of this. So on the left, you see what I was mentioning. I'm telling the model that I want the plus to have priority over multiplication. But at the bottom, you see that even though actually the output, in the output, the model seems to have understood, in practice, it didn't. So on the left, you have a mistake. On the right, instead, you have a similar example in which we are using one-shot learning, in this case, with the structure of the example we are providing being the same as the one in the formula we are requiring the model to simplify. So the nice thing here is that the structure of the equations that we are providing for few-shot learning has a strong impact on the model performance. So this is something worth further research. And this is another example with non-standard operations that in this case are defined as tables, and basically the model fails to look up at the table. So I want to conclude just with mentioning some future research directions we are going to pursue. So apply category theory also to explainable AI, extend our certification, network certification framework to consider reinforcement learning, so not start from a fixed network, but also learn it by reinforcement learning. Work more on defining expressive graph neural networks and try to include them in diffusion-based graph generative models.
Right.
And of course, to extend the case studies. These are the ideas, but now we want to actually include the domain knowledge and the graph models in them. Okay, this is all. Thank you.
So is Marco here? So please come here while, if there is any question to Nicolò. No questions? Okay, thank you. Since we don't have much time, I guess we can go forward.
Thank you. So I'm going to report about the project MyPM, which stands for Multimodal AI Techniques for Process Mining. The notion of multimodality is a sort of rephrasing for integrative AI techniques for us. Since I don't know how many of you are familiar with process mining, it was mentioned in the presentation before, I want also to give you a brief overview of what is going on in that field and how this connects to the project and to integrative AI. Oh, sorry. Don't know what is happening. The term process science was coined recently. There is a very interesting position paper that was published this year in the newly established Journal of Process Science. And if you look at what is going on there, there is finally a combination of what we were used to call business process management on the one hand and process mining on the other hand. So there is the idea that we have to capture processes in an organizational setting in order to represent what is happening inside the company and how the company organizes internally the work. And this is the realm of business process management, where you typically elicit these processes and then you want to manage them. More and more, while we execute these processes, we are collecting data, digital trace data about what is going on, and that is where data-driven techniques come into play, where you want to analyze this data and provide insights about the actual execution of processes, which is called, when the data have the form of traces executed during the execution of processes, is called process mining. So this is the BPM life cycle, and if you look at what is going on here, there is a process discovery phase where you want to elicit these processes, then you model them, you configure information system to support the execution for the domain experts and the workers of the company, and then you have the actual execution. And there are, again here, two important pillars that we are obtaining. On the one hand, we want to make explicit descriptions of these processes, and on the other hand, we are collecting execution data about them. So let me go a bit more into details. So what does it mean to elicit a process model? It typically means you do conceptual modeling in an organization. You have process analysts that go there and talk to different stakeholders in the company. And what happens is, and that's one essential feature also of this process, often when we talk about processes, we talk about diagrams like BPMN or that capture the control flow of what is going on. But if you think about it, even if you have a focus on the process, there are many other dimensions or perspectives that are coming into play. There is, for example, here the data perspective. So processes operate over objects that have mutual interrelationships. And often all this complexity is simply stripped out and you only focus on control flow, assuming that you have some notion of object that you are not going to describe further. You can see here in the top left a decision diagram. You have decisions that are taken, and these decisions are taken partly based on the control flow, what you did in the past, but partly based on the attributes that these objects carry. So you must now be able to integrate perspectives. And then there is the point that obviously, as I told you before, you are executing this process in a real organizational setting. And if you imagine that the process is nothing else than a compact description of everything that you want possibly to see in the organization, separating it from instead what you don't want to see, then you can imagine that executing this process essentially means taking choices and evolve these objects over time. For example, I'm managing orders. Each order will take a route in the process, will have a different speed, decisions will be taken, and different ending states will be reached. And so here there is another perspective that comes into play, which is time, and is also how you are modeling the fact that, for example, in what I was showing here, some cases all ended up in the same state, and one ended up in another state. You may simply model this as non-determinism, or you may want to go more into quantities here, and, for example, introduce a stochastic perspective that helps you understanding which are the errors in the process and which are instead the parts that are not very often executed, right? This all brings to this notion of multi-perspective processes that are at the center of this project, right? So we have a backbone perspective, which is the control flow, but then we have these different types of data that may use different theories. We may have real numbers, we may have a relational database, we may have whatever complexity you can imagine, and there is this framework of reasoning modulo theories in AI that is crucial here. On the other hand, there is this perspective of uncertainty that may have, for example, to deal with modeling decisions stochastically, modeling the duration of activities stochastically, but we are also looking into other aspects, like, for example, fuzziness, different types of probabilities, etc. So one of the first main questions of the project is how to represent this formally, right? Considering the case where the backbone in terms of control flow is a Petri net, which is the reference formalism for representing, so to say, procedural processes, or if you want to work on declarative, declare was mentioned before, there are linear temporal logic on finite traces and variants of these logics that are the foundational basis of declare. And then we want to have techniques for model analysis. So reasoning, dealing with these different perspectives. Then there is the second pillar, right? So there are the event logs. So let me go briefly through those. What are the types of data that we are interested in process mining? The time dimension is essential, but we don't have like time series, at least you know, to represent the execution traces. We may have time series to represent connected phenomena. So we essentially have data like those that you see here. These are data from a triage in a hospital. And as you can see, what we are collecting here is what are the activities that are executed, when they are executed, by whom these events are generated, and on which objects this is going on. So for example, this case ID that you see here, this may be the patient identifier in the hospital. And why is this so crucial? Because if you now join all the events that deal with the same patient, you can see the trace of the patient through the system, right? And so we have again here multiple perspectives that are coming into play. There is time, there is different types of data, there are objects. And for standard processes where you can imagine that every object is evolved in isolation, there is a standard by IEEE to represent those. But reality is much more complex than that. So the community had a recent shift, which was also recalled before, is typically called object-centric process mining or object-centric process modeling, where if you consider a large variety of processes, you never have single objects that are evolved in isolation. Objects are all interrelated, and the interrelationships may be of a very complex nature, like, for example, many-to-many. So you don't have anymore that an execution focuses on a main object. Every execution focuses on a collection of interrelated objects that are co-evolved. So, for example, you may have one order that has multiple items. Each of these items is packaged with other items that may belong to the same or different orders. So there is the problem of how to represent this complexity. And then also, when you approach the problem from the data point of view, there are different forms of uncertainty that you have to be able to represent. Here you see a probabilistic form of uncertainty, like some event happened, I'm sure that the event happened, what I'm not sure about it is what was the activity that was executed. And you may want to, you know, represent this probabilistically, like, oh, 70% chance this was accept order, 30% chance this was reject order. And I'm also not sure exactly about the timestamp. Okay, so that's a type of uncertainty you may want to capture. We also looked recently into another type of uncertainty. It is also very relevant to try to interconnect these kind of reasoning techniques in a neurosymbolic setting. What if events have instead a fuzzy nature? So you see here a person that is doing two things at the same time with different intensity, right? You may want to capture here, look, the person is more focused on cooking, but the person is also working in parallel, like he's having a call while he's cooking, okay? So the type of uncertainty that you have here is not the type of uncertainty that I mentioned before. So you have now to deal with fuzziness and probabilities. Process mining is meant to connect the two, right? And that's where we are in the core of the project. So if you go back to the origin of process mining, it was really, I want now to connect these process models with the event logs. And what is that you want to do in particular? You want to automatically discover process models by looking into this data. You want to be able to generate new traces, but looking into the models once you customize them on top of the data that you have observed. You want to be able to enhance the description of the models by using information that you have from the data, like, for example, again, frequencies and times. But you also want to accept the fact that reality may deviate from the models, and so what you want to do is conformance checking. You want to identify if you can replay the data on top of the model, and if not, where are the deviations and where they do not agree. And what we are doing in MyPM is approach various problems in this spectrum, not with ad hoc algorithms, but by resorting to different AI techniques that are combined together. Okay, so that's the core of the whole project. Now, I mentioned these process mining techniques, but you may even go beyond that, right? So you may want to focus not only on what happened in the past, so data that you collected about past executions, but also try to suggest things regarding the future, right? Like what is likely going to happen? Can I give recommendations on how to operate on this? And that's where also other techniques, mainly from machine learning, come into play, right? Like predictive analytics. So I want to conclude in the last 3 minutes by giving just some highlights on technical things that we are doing. The first is providing new models that extend LTLF on the one end and standard Petri nets on the other to be able to represent these different types of data, how they interplay. And there are various complexities here that emerge because, for example, when you are in a situation where one order has multiple items, you may want to progress the order in its life cycle only when all its items have progressed. So you need also advanced forms of synchronization that are not covered by contemporary models. And as I was telling you, we want to reason on these models. So an approach that we are applying here is behind the scenes encode everything into SMT. So you get logical formulae that are representing the execution semantics of these models. And one main focus that we are having in the project is in particular use SMT to solve these conformance checking problems. So you encode the specification in SMT, you encode the trace that you're observing in SMT, and you frame the problem of trying to align them as an optimization modulo theory problem. And you can discharge these to solvers. We are doing pretty much the same, considering forms of uncertainties. So here you see a Petri net with stochastic components. So when you take a decision, you have a stochastic variable that is representing that. And there are various queries that you can pose over these models, like what is the probability that a trace is going to be produced by the model, or give me all the traces that together cover 50% of the probability space of the process. And to solve these techniques, behind the scenes, you typically need to resort to model checking on the one end to deal with the time aspect, and Markov chain and related techniques to deal with probabilities. This is also in turn relevant for conformance checking. So an interesting feature is that reasoning here provides also core components for doing process mining. If you have this uncertainty coming into play, and you have your process coming with a distribution of probabilities, for example, over the traces, you may take a log, look into the frequency of traces that you have in the log, and then try to merge the two, right? So you try to basically compare the probability distributions and get a form of what is called stochastic conformance checking. Last two highlights. On the data part, there is an ongoing effort to define a new standard for representing these processes executions where you don't have traces anymore, but now you have evolving objects. And there are various approaches here. One is called event knowledge graphs, where the focus is now events refer to multiple objects. We must be able to represent this. This is not able to describe, though, what is the actual impact that these events are having in terms of the objects. Like, when I create an order, I'm instantiating a new object of type order. And when I'm canceling the order, I'm destroying certain relationships, right? This is instead very widely studied in databases. For example, now there are formalisms like temporal property graphs, where you can represent how objects and relationships evolve. And what we are trying to do is merge these two perspectives together in an integrated representation. Last highlight that I also want to emphasize, I think is particularly important, not only for the topic, but also because it was already a fruitful collaboration between Bolzano and FBK. So this is joint work with Andrei Buliga, Chiara Ghidini, myself, and Massimiliano Ronzani, is entering more into the neurosymbolic aspect of some of these process mining tasks. And one task that is very relevant is computing counterfactuals, because you want to explain about certain phenomena that you are observing through the data on the one hand and through the model on the other. The problem that you have there, which was also mentioned in the previous presentation, we may have background knowledge that we want to incorporate. So give me a counterfactual with all the characteristics that a counterfactual have, but make sure that this counterfactual is obeying to some background knowledge that is expressed, for example, in LTLF. Now, there are various techniques to do that. We wanted to have a technique where this is guaranteed logically, so not, only probabilistically. And so what we did was combining techniques based on genetic algorithms to generate counterfactuals, making sure that looking into the background knowledge and extracting information from the automata that we can build given an LTLF formula, we could only allow the genetic part to mutate things in such a way that the background knowledge is respected. And this is going to be presented next month at AAAI. That's pretty much what I wanted to say. Thank you.
So please, the next speaker, questions? Can you tell us something about the complexity? Because you are, I mean, working with many objects simultaneously, and so this is going to be a problem, I guess. Meanwhile, if you leave
sure.
the stage to...
So essentially, the way we approach these problems is like these problems are not only very complex in general, but many of the things I showed you are completely undecidable. So the idea is first we try to characterize the more general setting, and then we go deeper into fragments. And we are trying to find fragments where we can say more about the complexity, but also fragments that even though the complexity is still quite terrible, we know that these solvers go quite fast, right? Is a bit, if you think about SAT, right? There are many instances where even though we know they are NP-hard, SAT solvers are very good. This is like lifted now to the first order. So SMT solvers go quite well in many settings that, you know, complexity-wise are quite terrible. So there is also a lot of experimentation that we are trying to do to confirm or disconfirm this. Okay. Yeah.
Thank you very much. So Riccardo.
Okay, so good morning, everyone. So this project is about the integration of AI techniques and tools into a robotic platform, in particular in a semi-autonomous surgical robotic platform. So robotics is per se a multidisciplinary area, and if you add also the AI, then and the complexity increases a lot, so that's the reason for which you see a lot of people here, experts from robotics, AI, computer vision, and also we have a professor in moral philosophy and a professor in philosophy of law, just to have everything in a single shell. So I will start first showing our experimental setup. So what you can see here is a Da Vinci research kit. So it is a surgical robot for a minimally invasive surgery, and we have on top right the surgeon side, so where the surgeon controls 2 joysticks, and the big picture is the patient side. So now we have a mannequin, and usually there is an assistant surgeon next to the patient. What we want to do is actually to substitute the assistant surgeon with 2 robotic arms holding standard laparoscopic instruments. So, and the goal is actually to design the overall architecture in order to understand the procedure, understand what the surgeon is doing, in order to help him or her in, since there is this gender balance, so we have to pay attention now, how to proceed with the procedure. If there is an assistant surgeon, then people call this kind of architecture solo surgery, because you need just one surgeon. And in order to do that, we have to integrate a lot of technology in terms of perception, the environment that is changing over time. You have to develop modules for the situation awareness and the decision making to help a surgeon with the right action, in the right time, with the right instrument in the right place. And then when you have this decision to automatic plan the task and of course deploy it. So these are the list of objectives that we have in this project. Of course, we don't start from scratch. We have a lot of results from a previous European project that ended a few years ago. We are just refining and improving the architecture that we already have. So the goal, in particular, the goal in this project is to improve the detection of laparoscopic and robotic instruments using the video streaming from the endoscope, the phase segmentation of the procedure, because this is a key information that we need in order to know what to do next. Then continuously update the model of the anatomical, the 3D model of the anatomical scenario, because of course during the intervention, the scene changed completely with respect to pre-operative information. And then to provide a better human-robot interface to the surgeon, developing new tools. And what we are tackling right now is the knowledge representation. This is actually a very important and quite difficult task. So we have to integrate the preoperative knowledge with actually what we collect during the intervention. And that is actually quite demanding, because based on this knowledge representation, then we have a good or a not so good decision maker. And then at the end, we plan to have a sort of white paper on the ethical aspect and on the legal aspect. So we started from the mechanics, I would say. So I know probably you are not much interested in this part, but in order to execute some task in an autonomous way, you have to bring some sensors closer to the instrument. So we designed smart surgical instruments. So these are some of the mechatronics part that I can skip. And I would like to show you this video. So one of the first tasks that we are tackling is to autonomously select the proper tools and change the tools. Of course, the position here is known. What is not known is the position where we have to insert the tools in the belly of the patient. You see that there is that plastic, white plastic. This piece of plastic is called trocar, is from where the instrument enters into the belly of the patient. This is not known. So we have, thanks to the camera, to detect the trocar, to detect the belly of the patient, and then to plan the trajectory in order to insert in the proper way without harming, of course, the mannequin or the real patient. And so these are the kind of things that we are working right now. So you see there is the integration of a lot of standard robotics with a lot of computer visions. But that is not, this is not enough, and because of what we want to do is also to plan the trajectory in order to satisfy what is called the remote center of motions. So this is the trocar from where we insert the tools. But of course, you have to pivoting around this point. You cannot translate, otherwise you harm the patient. And so, since the position of the center of motion is not known, we have to identify, to detect it, to estimate it, and then to plan the trajectory for the robot that move the tip of the tools where you want, without, satisfying the remote center of motion. And so, this is the standard architecture that we are defining. So you see different controllers according to the phase of the procedure. And this is standard robotics. Now, where the AI came to play, the first thing is about the phase segmentation. It is clearly important to know in which phase of the procedure we are to make the right decision in order to help the surgeon at the Da Vinci console. And this is not, of course, a new topic, but in the surgical domain is quite challenging. There are not a lot of data set, and what we are planning is also not only to detect the current phase, but also predict the next phase, because sometimes the phase changes because we are, with our autonomous tools, to change the phases. So it is a little bit different than the usual problem. So these are our architecture that we have developed. At the moment, we are working on a data set on called cystectomy, because it is available. There are a lot of annotated data, but the procedure we are focusing on is the prostatectomy, where there are no available data set. We have our own data set with a few procedures on real patient and on mannequins. And the last point is actually the more important. So the phase segmentation or anticipation must be done in real time, take into account that in some cases is the autonomous system that triggers the next phase of the surgical procedure. So it's not just a passive analysis of the video streaming, but it is a little bit different. Another thing that is very important is the tool segmentation. We already have algorithm for the semantic segmentation of the anatomical scene, so to know what we are looking at. But also what we want to improve is the tool segmentation that is needed to understand the scene and of course to localize precisely the tools. This is the classic picture for automotive, and what we are doing is the same things in the surgical scenario. We are using SEM2 in order to detect the different tools, in particular the tools that the surgeons is moving, so not the one that we are controlling, because of course we know where the tools that we are controlling are. We don't know where the tools that the surgeon is moving, where they are. And so this is what the techniques that we are developing in order to know where the tools are and later to predict where they will be in order to avoid collision with our tools. Another things mainly related on computer vision is on the estimation of the trocar, so this piece of plastic. And this is quite important, rather important, because when you know the pose of the trocar, we know also the direction for the insertion of your tool. So you have to integrate a lot of 3D pose estimation, and another key aspect is the end-eye calibration. So integration of where, the frame of the camera with the frame of the robot in order to insert accurately the tools. So, as I said, we are working, colleagues are working on the ethical and the legal aspect, and we discussed a lot yesterday about all the legal implications about the AI in industry, but of course it is even more important in the healthcare domain. And I would like just to highlight a couple of things. We have to understand in particular how autonomous or semi-autonomous systems interact with the medical personnel, and in order to be sure that our algorithms are reliable, trustworthy, and explainable, the standard things. And we follow here a bottom-up approach, so we are planning to deliver a sort of survey to surgeons in order to understand their needs and how they see this kind of technologies. From the legal aspect, this is even more important, in particular on the attribution of conduct and consequent responsibilities for the subject, in this case the surgeon, conditioned by AI and conditioning AI. So this is another quite interesting area, in particular now that there is the AI Act that appeared last year. And okay, so I don't want to, in the interest of time, I don't want to go on with this detail that of course are not my topic. I would like only to read the third point. So the complexity increases when technology intervenes between a person action and the result, making it difficult for the patient to prove harm or negligence. So when everything is almost autonomous, for a patient, it's not so clear if he has to sue the surgeons or the company that produced the robot. So, and this is quite, quite important. Well, so in this slide, just the impact that we expect. I will only to focus on the third one, on research. So most of the technology that I saw yesterday and also today can be applied on a system like that. So if you want to try to implement your techniques in these peculiar scenarios, we are more than happy to work with all of you. The next phase are to improve our situation awareness and decision-making module, and to describe the knowledge in a much more efficient way that we have right now using state chart, and of course developing a better human-robot interface that not only provide force and visual feedback, but also speech recognition and augmented reality features. And that's all from my side. Thank you.
So while Vittorio comes to change, okay, there is finally a real question.
So meaning the other were not real. No, just a quick question, but when you use the Da Vinci, you have a localization system on board for all the links, right? So why can't you get the information of how it is positioned directly from the encoders of the system and with kinematics, etc.?
You can do that if you have the Da Vinci research kit. So in the lab, you can do whatever you want. If you register all the robots, the Da Vinci, with your own robot, that is fine. But this is actually what is not going to happen in real life, because in the operating room, you don't have access to this data. The company doesn't give you access to this data. So you have to estimate the pose of the instrument by using the only thing that you have, the video streaming. So in the lab, you can do what you mentioned, but we are planning, to do something more ambitious.
Okay, thank you very much. Let's go forward. Vittorio.
Okay. Good morning, everyone. This is actually, I'm presenting my project, which is a joint work between me, Mashid Shiri, and Chidembe Yan of University of Verona Department of Computer Science. So first of all, we want to describe in a few slides which is our project, which is called TALIM, Transfer Adaptive Learning in Perfect Multimodal Data Scenarios. Essentially, we start from the consideration that so far AI systems, or let's say much better, deep learning techniques are good when we have large, well-annotated data. But in reality, what we have to deal with in the real world are often imperfect data, which means that the data can be unlabeled, can be partially labeled, can be noisy. In terms of labels, can be just a bunch of data, or also class imbalanced, or even worse, having some bias. So one can say, okay, you can annotate this data, but annotation is costly and error prone. And of course, costly because billions of data cannot be annotated manually, and also if you use automatic techniques, they are not quite reliable. And the other consideration from the other side, I profoundly believe that if you have to deploy an AI system in a real application, it's not a good idea to deploy just using a single sensor, depending on the kind of applications. But if you think, for example, autonomous driving, if you can base only on cameras, could be in the limitations. So we want to push forward the idea to have multimodal data to ensure a reliable and stable goal fulfillment and behavior. So a multimodal artificial intelligence system can in a way try to cope in a better way with more flexibility and more reliability over a larger number of applications, enhancing the robustness. So the objectives of our project is just to investigate in multimodal learning through the lens of imperfect data. And more technically, what we'd like to explore is a set of self-supervised learning methods for model pre-training and leveraging multimodal data. We want also to address transfer learning and domain adaptation tasks in multimodal setting. These are actually quite, I don't know if you are familiar with transfer learning, domain adaptation, domain generalization task, maybe more later. And also distillation paradigm, and especially using teacher-student architecture, trying to evaluate the importance of different multimodal data streams. So to give more importance to one data streams over another depending on the specific task we have to solve. As a whole, our idea is to try to focus on data augmentation, especially also data generation, to cope with data imperfection. So what we want is essentially try to control the generation and augmentation processes to improve the task performance. And yeah, the idea is essentially to, the main strategy, the overall strategy is trying to understand how to control these data transformation techniques, or even generate suitable synthetic data to correct or rebalance the problems derived from the available data sets. So in this context, our work is essentially try to address a self-supervised learning approach based on dual contrasting learning loss, based on CLIP architecture. So for many of you, probably CLIP is not familiar, but essentially is an architecture, is a technique which is trying to pair image and text data. And we also address this domain shift, adopting techniques called adapters and learnable prompts on this CLIP model. So this is actually the outline of my presentation. I try to introduce first the task, which is medical anomaly detection, and then some explanation of the data, and a few information about the proposed method and a couple of results and conclusions. So let's start from the medical anomaly detection. This is actually is becoming a big problem. It's a big problem. It's becoming much important lately in these last years. So it consists essentially in identification of unusual patterns in medical data. This unusuality, this abnormality is essentially a challenging task, because you can see, for example, from the example here on the left, that you have a normal image, and you see, anyway, a pathology on this image on the right, which is quite different. So you have to understand if it is a pathology with respect to the normal organ you can see here. But if you, anyway, see on the right, this another, for example, signals, which is essentially a signal can be heart rate or whatever. This is actually the normality, but in the plots below, you can see some noisy signals, which essentially is the same, a little bit more noisy for whatever reason, and this is much different. So it's really an issue to understand which is an anomaly and not confounding with some noisy behavior of the signal you are trying to acquire. And even worse, if you have to deal with a few shot means that you don't have this large amount of data, but you have just a bunch of data, for example, 2, 4. We arrive at 16 and no more. And this is actually even a worse situation, in the sense that you want to identify these abnormal patterns in the data, having the availability of a limited labeled data for normal and abnormal. In some cases also you have only normal data. So you have to infer in some way which is the abnormality with respect to the few normal data you have. If you think at the biomedical or healthcare applications, you can think essentially that we are in this condition. So we can have potentially many data for the normality, but abnormality could be also not so common, let's say fortunately. So there is this class imbalance between normal and abnormal, considering abnormal, for example, as a pathology. If you are inserting in this reasoning also the multimodal, we want also to generalize over multimodal data, which means that we have to deal with different modalities and try to detect the anomalies depending on the modality, or let's say independently from the modality. And the different biomedical data we can have is just a difference in appearance, structure, imaging across the various modalities. again, this is actually regarding the nature, the very nature of the data, but if you are going to the anomaly, we can see that, for example, there is not only one type of abnormality, it can be also different types, and we have to generalize this behavior from just a few examples. In some cases, you can have access to auxiliary data sets, but also in this case, these auxiliary data sets are not enough to improve the performance. So in the end, our approach one approach which is dealing with multimodal, few-shot medical anomaly detection task should address this data scarcity, take into generalize and to cope with variabilities to have these robust solutions and flexible, depending invariant to modalities and type of abnormalities. This is an example you can see here, and for example, from the first two rows in the top are normal images, multimodal. And you see, for example, here you have some MRI techniques and CT. You have here the retina. This is histopathological images, which is a CT for the chest. And you see this normal stuff. You see very different part here between the two. And if you go to the last row, you can see here the abnormalities. And the abnormalities you see, depending on the modalities, are very different each other, depending on the task. So we have to deal with also different anatomical regions because we have brains, we have liver, we have retina, we have cells. And for this reason, we have to, in a way, ask some help, and in the last years, the help and the support we can have in this kind of models is about the text. So we want to leverage visual language models, and so we need some sort of textual annotation, language annotation of abnormalities, but also in this case, the definition of abnormalities, the textual abnormalities is not so easy to make because the abnormalities also from the point of view of textual information are not similar to each other. So that's why we wanted to leverage a visual language model, and we use some this clip-like architecture. The clip architecture is interesting because in trying to pair textual and visual information, and especially it is trained on a very large number of images, natural images. So we have to, in a way, transfer this knowledge acquired by these natural images to biomedical domain, multimodal. And another task is that in this case, for the clip case, the images are essentially at object level, so they are trying to pair foreground object versus the textual information. But in our case, we have, in a way, not only object abnormalities is localized, but can be also distributed, so it's this kind of problems. So our proposal is essentially to have this two-branch architecture based on adapters for few-shot anomaly detection and segmentation also. And we introduced this another loss function which takes into account image text learning, and we are introducing an alternative loss to try to cope with these problems in a classical benchmarks. Let me, in a way, just go through quickly to the kind of data. We have here liver CT, so computerized tomography, brain MRI, histopathological images, X-ray of chest, and this, the last one in the bottom, are retinal images. Previous work, I will skip because it's not so important, but this, let's go to the main, the core of the work, which is essentially using vision adapters and learnable prompts in the context of your bench architectures. So the vision adapters, you can see here the architecture. So on the top, you have this vision encoder and the text encoder, which are frozen, which are pre-trained. This is actually the encoder text and vision from clip. And the text encoder is taking an input to the normal and abnormal prompts, and produce embeddings, which are inserted in these CL modules, one for each level of the vision encoder. These CL are contrastive learning modules, which take in input not only the embeddings from the text, but also the embeddings coming from the vision encoder, from the normal, yes, this one, and the abnormal cases. So N stands for normal, and AB stands for abnormal, and A stands for adapters. So the idea is to trying to leverage, so to learn the learnable prompts, which are this V and W, concerning separated between normal and abnormal. And also we took also the adapters, which are anyway, I tell you in a minute. Try to put all together, try to pair in a proper way normal and abnormal prompts, learnable prompts and embeddings on the visual information, aggregate in some way to give segmentation and classification results. Why adapters? Adapters are simply very tiny neural networks, and they are used to customize vision language models to a new task, to a new application, without retraining the entire system. And this is actually why we use this. So we try just to learn from the adapters, and then the learnable prompts is essentially included to align the prediction with domain specific of the biomedical domain. And this is also important for transfer the clip potentialities to the specific domain of biomedical segmentation, that multimodal biomedical segmentation and classification. These are the contrasted learning. Essentially, we have this matching between the adapters, normality, considering also the visual information, and the T is the textual embedding. And the contrastive is between this normality and the abnormality between text and images. And also, we have the abnormality branch, which is doing the same, but the opposite sense. So we are trying to match the abnormality together and try to get far away from the normality stuff. So in a sense, this is actually trying to match the normal and abnormal behavior, trying to localize exactly the embeddings and improve the information. We combine these two results, and we aggregate in a multi-scale aggregation in order to have, and we learn on the basis of this two-branch architecture. This is the clip loss, which is essentially the loss based on clip, the classical one, and then we add other two terms, one for classification, which is simply the cross entropy, and instead for segmentation and classification, we add two classical other losses, which are the dice loss and the focal loss, which takes into account the imbalance of the data classes. And that's it. So this is the results in classification and segmentation. AC stands for classification, AS for segmentation, and we have the beta results, which are at the bottom here, also compared with the state of the art. And this is also the results in average concerning, and we have also the 2 shots. 4 shot means that we are still using just 2 images for normal and abnormal. That's why it is quite impressive. The results are so good with just very few information. And then Alessandro is in a way. No, the conclusion is that, okay, so I try to, we worked in this clip-like architecture for anomaly detection scenarios with normal and abnormal data. We leverage on this. We have an overall improvement. And for future work, we are now trying to address the cross-modal scenarios. So far, these results are in a single, in a way, unimodal stream, but for all the data. Now we are trying to understand if the information coming from other multimodal data streams can help to the anomaly detection of others. So this is called the zero-shot scenarios. And also we want to leverage a generative approach to synthesize abnormal samples in few-shot settings using only normal data. So we want, in a way, generate abnormal data in a controlled and more automatic way to improve our performance. That's it. Thank you.
Okay, so is there any question while there is the switch for the final presentation? So you could also use, I mean, there are approaches using Q-former. It's basically similar. What is the main difference? I guess the contrastive.
Sorry. I'm not so familiar with Q-formers. I know they exist, and yeah, maybe we can have a look to see what happens there. But this is based on linear architecture, which was used in this way. We try to adapt it in a way. Let's say fine-tune the performance based on this clip architecture. Yeah, Q-former, yeah, I know the existence, but sorry.
Okay, thank you. So we go to the final presentation.
Thank you. Okay. I'm going to present very quickly the project Harmonia, which is focused on developing I don't know what's happening. Okay, perspective taking. Is there something? Okay.
We were thinking that you are going to fix the problem. Okay, so it's the adapter thing.
Is it the adapter? Okay.
So meanwhile, who was losing this? Is it yours, Vittoria? No? Okay. Lost.
Okay, maybe it's working now. So yeah, about developing knowledge-enhanced perspective-taking large language models for inclusive decision-making. In this project, which I'm coordinating, we have a multidisciplinary team, including people of different groups from University of Turin, and in particular colleagues from my department, computer science department, covering different competencies from natural language processing to semantic modeling, and colleagues from the Department of Economics and Statistics, which are especially interested in behavioral phenomena related to, in this case, to urban spaces. And we, thanks to the funding of FAIR, we also had the possibility to hire a junior team of researchers, mainly postdoc, and one PhD students to support our activities. Basically, Harmonia is focusing on the goal of contributing to rethinking relationships between citizens and public administration. This is our main focus. And in particular, the idea is to rely on the use of large language models, but working on enhancing them with relevant knowledge for supporting informed and inclusive political decisions in public decision-making processes. And in particular, the idea is that there is a need from the stakeholders' perspective about understanding how to use such a very powerful technology in order to improve decision making, and especially making it inclusive, and especially because a good policymaker usually address this task trying to understand from many kind of data that are available to the city halls, for example, how to improve, for example, a service, taking into account that there are different community needs from different categories of citizens. So our aim basically is to leverage this very large set of heterogeneous data coming from also opinions that citizens are expressing on social media, but leveraging also data which are usually the ones exploited by policymaker in order to take a decision about how to intervene for improving some services. And the idea is to understand how to exploit also a new approach which are studying in Torino, which is called data perspectivism, in order to develop large language models which, informed by this data, are able to somehow adapt the suggestion to the policymaker with respect to the needs of different populations, with the idea that somehow an inclusion, the decision-making process must take into account that given some kind of discomfort signal that can be detected by the policymaker, it is possible that different perceptions from different categories of citizens, like women or men, if we think about gender, that could have different behaviors and needs with respect to a service that can be related, for example, to mobility, and or other people which, for example, is retired, can have different perceptions about the service and different discomfort, and also the stakeholder that must intervene with the decision making, trying to change something, can take into account all these different data and the different perspectives in the decision. So there are mainly two objectives in the project. One, it is related to the interaction with the city hall of Turin in particular, in order to get information and data about verbal and non-verbal citizen interactions with urban services, in order to have a base of data about behaviors, social issues, and also possible nudges to change behavior. And to model all such heterogeneous knowledge and make sense of this heterogeneous knowledge by exploiting semantic modeling, basically. And so in the first step of the project, as we will see in a moment, the key points were the identification of some case studies together with the City of Turin City Hall, and the part of semantic modeling, which will lead to the creation of a knowledge graph that will be released at the end of the project. Then there is the other part, which is more related to the development of these large language models with perspective taking, which will leverage on the information collected in the first part, and with the idea that such perspective taking large language models will reflect different communities' viewpoint, and the idea, we are already exploring a different approach in order to inject knowledge in large language model in this perspective, in particular retrieval augmented generation approaches, and we plan to investigate also more sophisticated knowledge injection approaches. Of course, there will be also a part of evaluation that we will be of the outcome of this enhanced decision making that will be taken together with city councillors that were that we were contacting in the last months, and that are happy to be involved in order to evaluate the usability and the reliability of the technologies that we will develop. And also it will be interesting to see how this new methodology to enhance the decision making will lead to results different with respect to what we get by using, for example, standard econometric modeling, which are the methods exploited by our colleagues from Department of Economics. About case study identification and data collection, I would like to just to share that we had contacts with different departments of City of Turin, in particular assessorato alla transizione ecologica, digitale con delega ai trasporti, parcheggi e viabilità, so Department of Transport, and assessorato al welfare, diritti e pari opportunità, so Department of Equal Opportunities, and we also had data from a regional school office, and in the end, after all these kind of discussions with these entities, we decided to focus on a main core case study, which is public transportation in the city of Turin, even if we collected data also on educational services and public housing in order to have also interesting intersection on other kind of service that can be provided and enhanced by our system. About data collection, which has been driven by the choice of these case studies, we collected data about the interaction between citizens and urban services, in particular in relation with mobilities, in order to develop a map of possible discomforts that we would like to address. And these data are heterogeneous. We were identifying some social media sources that could be interesting from this point of view, like we were collecting data from Reddit, Facebook, and Twitter about urban services related to mobility, housing, in particular in the city of Turin, in order to have a kind of social sensing about these issues. But we collected also data from the department that were involved in that are involved in the project, in particular behavioral data, statistics, census data, and also textual data in forms of complaints of the citizens with respect to the services that we would like to improve with our with the help also of our tool. About semantic modeling, we are in the process of developing a semantic model in order to integrate all this kind of information, also trying to catch different perceptions and opinions of different categories of citizens on services that we want to improve. And this is just an example of these perceptions can vary, like having an overcrowded bus in the morning can be highly problematic for high school students and not problematic at all, for example, for retired people. This is just a simple example of what we can model. And another activity was related, since our decision maker will interact with LLMs in Italian, there is the issue of what is the state of the art of the kind of model available with respect to interacting with the Italian language, which is something we were working also in the context of a benchmarking initiative. And I would like just to mention the Calamita Challenge that was that I participated to this kind of benchmarking activity, which is supported by our Italian Association of Computational Linguistics. And I participated also to another initiative in collaboration with SPOC2, in particular with the group of Bernardo Magnini, in order to create a benchmark starting from adapting shared tasks that were built in the past in the context of the Validità evaluation campaign based on native datasets in Italian. And This has been something to be done in order to understand which kind of LLMs we will use among the available ones, which are the more promising, just to give an idea about the kind of mapping of abilities that we are doing in these benchmarking activities. That there are many different abilities of large language models that can be involved, and also related, for example, to gender gender fair languages, which is something that we tested also together with a group from FBK. And you can take a look about all the kind of tasks that have been, for example, evaluated until now in the context of these evaluation campaigns. The other point, as I mentioned, is the innovative point is to test in this kind of application context the perspective approach that we are trying to follow in general in Turing, both from the point of view of natural language understanding, but in this case it will be interesting to test the possibility to develop this kind of approach in a natural language generation context in order to try to make the model capable to support policy decisions with a kind of point of view informed by the different different shaping that we will have with respect to categories of citizens. Just a very quick overview about the pipeline that we are following concerning the RAG approaches that we are testing. One of the point is to use to make sense of this heterogeneous data, and I will say just something in a second. This is just a sketch, a kind of possible scenario that you can imagine to deal with our kind of approach. So, for example, a policymaker could need to reshape a line of a bus for part of the rules, and can interact with our enhanced LLM in order to get suggestions, considering that maybe he wants to know if there are already categories which are of citizens which are are releasing a signal of discomfort, and maybe in changing this route he would like maybe to favor such categories of citizens which are at the moment disadvantaged, or at least want to be aware about the possible pros and cons that comes from different decisions that can be done. And the idea is that all the information that we collected about mobility in the city and about perception of citizens with different belonging to different categories can be exploited by the retrievers, and in order to inform different large language models which enact as, let's say, different categories of citizens in terms of encoding their perspective in the suggestion that will be delivered to the policy maker. And this will allow, hopefully, the policymaker to orient the decision that in a way that improves the comfort of a citizen, or at least it will be bigger awareness about which categories of citizens will be advantages by certain choices, for example, also in a simple case like changing the route of a bus. And decision making is never one size fits all, and the idea is that also in the communication of these different possibilities, it will be possible to explain in a transparent way also to the policymaker which were the data that were exploited in order to orient a given suggestion, and also maybe the language of the explanation could be tuned also in terms of gender-fair language if this is something which is of interest of the public administration. Just a final word. Actually, we are working on the issue of making the heterogeneous data homogeneous, and one approach that we are testing at the moment is verbalization, which seems to be quite a promising way to try to make the data that we have, which are not only textual and verbal, verbalized, in order to have also the possibility to have a better comparison across different kind of data that we are trying to use in this kind of project. And thanks, and sorry if maybe it was taking a bit too long. These are just some first results that we're publishing in different venues in computational linguistics.
Thank you. So any question to have? Okay. Wait.
Okay. Thanks a lot, Viviana. Quick question. So clearly you can have, let's say, different needs and different perspectives, exactly, from the different stakeholders. And so the idea is that then the decision maker is left to find a synthesis, or the approach is also helping, for coming to a solution that is the one solving the problem for everybody.
Yes, the idea is that in the end, the answer is a kind of reasoned summarization of all the possible support that can be enacted with pros and cons. In my opinion, but maybe just my opinion, it's a bit dangerous to leave, something more to the machine. I would like to have the decision maker able to be supported by this kind of summarization of all the possible perspectives, but I would like to have the decision maker able to decide in the end with these materials, probably with better awareness anyway of what are the pros and cons, and explanations of which kind of data somehow that were available and that are injected into the model can be used. Because my impression is that sometimes there are many data available to the ones that must take the decision, but it's difficult also to know where they are, how to access them, and then there are maybe many mediation steps usually in this process. Maybe something like that can help the decision maker to be more aware about all this stuff, but in my opinion it could be nice that then they take the decision maker, which is not maybe a single, but a team of people, take the responsibility to decide what to do.
Okay, thanks.
Okay, thank you again to all the speakers, and I guess we are ready for coffee now. Thank you. And then Paolo will will bother you to finish with the coffee and starting with the new session.